All right, Whitaker, I think it's about time that we start.
Okay, sounds great.
All right, Whitaker, I think it's about time that we start. Oh, let's see. Although, if you have headsets, you might want to use them. I think I heard some feedback.
Oh yeah, I'm using them. Yeah, I've got them now. Do you still hear it?
Nope, it's good.
Okay, great.
So let's see. It may just be us today, at least for a large part of it.
Yeah, yeah. As we can still go through the lesson and um, yeah, yeah. Maybe people will stop by a little later.
Yep. There is something that I wanted to show you though. So let's see. I'm thinking of ways to motivate people um, to kind of enjoy these streams and participate in them. I know they're math streams, so it's a little bit more effort, right? Than just like a gaming stream.
Yeah.
So I came up with this idea of like a grade book, but instead of giving people grades, I give them EXP.
Oh yeah.
And
Oh, that's cool.
I mean, it looks like this if you can see the screen.
Oh yeah, I see it there.
It's not filled out
Oh
yet.
yeah.
I'll need to go through all the VODs and see how many exercises people have done. Um, but basically, it works like this. So they get EXP according to this formula. Attendance times 25, right? So you can get passive EXP. This is like the smallest amount you can get just by showing up. The most you can get is from doing the exercises, right? Like participating and whatnot. So
Yeah.
that's how you would really grind it. And then there's extra credit for like interacting on Twitter or giving me suggestions for how to improve the stream. And other ways of contributing that's not like directly doing exercises.
Yeah. Yeah. I like that. That's a great idea. Yeah. That would Yeah. Yeah. It's nice to kind of have that. Kind of makes it like a game in some sense, and it yeah, kind of provides an extra incentive, and yeah, it's also kind of yeah, kind of a fun aspect to it. So that's a great idea.
Yep. And then they can level up, based on EXP like a game. And they can rank up at certain levels. I'm thinking of giving out rewards for people who, have committed that long and they rank up. So like everyone starts off as like a level 1 adventurer. You rank up, you'll get a new Discord role. Eventually, I'll start giving them like art pieces. It'll take a while for people to get to this rank. So if you think about it, that would be like 250 exercises. So I'll give them an
Yeah.
art piece. Um, so on and so forth. This art piece is actually just $100.
Oh yeah. Yeah, I like that one.
Me too. So I think this should be good. Like it'll take a while for people to beat the game. This would be like 2,000 exercises. And then maybe for each book, I'll reset it. But I'll leave a mark by their name to show what rank they got in the previous book.
Yeah.
So
Yeah.
yeah.
Yeah, it's a great idea. Yeah, let's do it.
Yep. That's one idea for improving the stream. Hopefully more come. Welcome, Mr. Steph. So, for
Sure.
example, since Steph just showed up, I would add his attendance here. I'll need to go through and calculate based on the VODs, like the actual EXP. Or maybe I'll figure out a way to automate it so that it just reads these and applies the formula automatically. But I'll be doing that after the stream. So let's see.
Yeah. Yeah, sounds great. Yeah, thanks for coming, Steph. I'm glad to have you here.
Now, as for people who like join the stream a little later in the book, I know they're probably going to be confused. Like some of this looks like gibberish if you haven't seen the first few episodes. So
Yeah.
eventually, maybe I'll do like a tutoring stream on the weekend or something. Just like a really long one, like 10 hours to go over everything.
Yeah. 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 Yeah, I do something like that. Yeah, luckily I guess some of like chapter 2, I guess, doesn't rely that much on chapter 1. So I guess someone could potentially start in chapter 2 and still understand it. But yeah, later on, they would need to like get caught up on the previous material.
True. So one more thing is, at the end of each chapter, there's these exercises, right? Sometimes they're sprinkled in as well. But in terms of EXP, it's kind of like a huge EXP farm. I guess we could do some of them on stream, but we don't have to. Like, I could just take a screenshot and then in the Discord, I would post it in the extra credit exercises channel. A lot like this. And then in the threads, people could answer these, whichever ones they want, and they would get EXP for that. I think it would be first come, first serve. So if someone answers 8, then that won't be available anymore.
Yeah.
I'm thinking they would get 50 points for just attempting it and 50 more points if they actually get the answer right.
Yeah. Yeah, that's a good idea as well. Yeah, it's kind of an incentive to get extra practice.
Yep. I'm trying to figure out the like, what should the limit be for how many a person can do? Because if just one person does all of them, then that might not be good for the
Oh yeah.
community. Yeah.
Oh yeah. Yeah, maybe like I don't know, 5 or 10 or something like that.
Maybe some percentage of whatever's available.
Oh yeah.
Yeah. Maybe like if there's 10 of them available, I guess maybe you should be able to do 2 at most. So up to 5 people could farm it.
Yeah. Yeah,
um
that sounds good. Yeah, so that'd be like 20, I guess 20%.
right. And then I don't know, maybe after a certain point, if no one has farmed it, then you can just clean them up, you know?
Yeah.
So I guess I'll set the rules in the exercise rule channel once they're fully locked down.
Yeah. Yeah, sounds good.
Now let's see. Okay, now I think we could go forward.
Yeah. Yeah, this is a fun lesson.
Yeah, let's see here. I can start.
Okay.
So The language of relations and functions. Oh, actually, there was one more point. Um, hmm. Someone had suggested reading this ourselves and then trying to just teach it without reading it in this stream.
Oh yeah.
We don't have to do that this stream, but I'll show an example of that next stream, just to see what it's like.
Yeah. Yeah, that'll be good to try out.
But this time I'll just read it aloud.
Yeah.
Language of relations and functions. Mathematics is a language. So there's many kinds of relationships in the world. For instance, we say that two people are related by blood if they share a common ancestor, and they are related by marriage if one shares a common ancestor with the spouse of the other. We also speak of the relationship between student and teacher, between people who work for the same employer, and between people who share a common ethnic background. Similarly, the objects of mathematics may be related in various ways. A set A may be said to be related to a set B if A is a subset of B, or if A is not a subset of B, or if A and B have at least one element in common. A number x may be said to be related to a number y if x is less than y, or if x is a factor of y, or if x squared plus y squared equals 1. Two identifiers in a computer program may be said to be related if they have the same first 8 characters, or if the same memory location is used to store their values when the program is executed. And the list could go on. So let A equal 0, 1, and 2, and B equal 1, 2, and 3. And let us say that an element X is in A, is related to an element Y in B, and only if X is less than Y. Let us use the notation X, R, Y as a shorthand for the sentence X is related to Y. Then 0R1 since 0 is less than 1, 0R2 since 0 is less than 2, 0R3 since 0 is less than 3, 1R2 since 1 is less than 2, 1R3 since 1 is less than 3, and 2R3 since 2 is less than 3. Okay, I guess they're saying the R just means less than in this relation here between A and B. On the other hand, if the notation X, I guess this is like, what do we want to call this? R slash Y?
Yeah, or not R.
X not R, Y represents the sentence X is not related to Y. Then 1 not R1 since 1 is not less than 1. 2 not R1 since 2 is not less than 1. And 2 not R2 since 2 is not less than 2. Recall that the Cartesian product of A and B, A cross B, consists of all ordered pairs whose first element is in A and whose second element is in B. So A cross B equals the ordered pair X and Y such that X is in A and Y is in B. Okay, all of the ordered pairs. In this case, A cross B is going to be 0 and 1, 0 and 2, 0 and 3, because 0 is in A and 1 is in B, and so on. 1 and 1, 1 and 2, 1 and 3, 2 and 1, 2 and 2, 2 and 3. The elements of some ordered pairs in A cross B are related, whereas the elements of other ordered pairs are not. Consider the set of all ordered pairs in A cross B whose elements are related. Okay, related by this relation here, the less than. So 0 and 1, 1 and 0 and 2, 0 and 3, 1 and 2, 1 and 3, 2 and 3. Right, some of these aren't related because 1's not less than 1. 2 is not less than 1, and so on.
Yeah.
Observe that knowing which ordered pairs lie in this set is equivalent to knowing which elements are related to which. The relation itself can therefore be thought of as the totality of ordered pairs whose elements are related by the given condition. The formal mathematical definition of relation, based on this idea, was introduced by the American mathematician and logician C.S. Peirce in the 19th century. So the definition: let A and B be sets. A relation R from A to B is a subset of A cross B. Given an ordered pair XY in A cross B, X is related to Y by R, written XRY, if and only if X and Y is in R. The set A is called the domain of R, and the set B is called its codomain. Okay, so if the when they say the ordered pairs are in R, they mean that each of the ordered pairs like satisfy the condition for R to be true, which is that the left is less than the right. That's what it means for the ordered pairs to be in R. So let's see. The notation for relation R may be written symbolically as follows. XRY means that the ordered pair X and Y is in R. The notation X not RY means that X is not related to Y by R. So X not RY means that the ordered pair XY is not in R. So
Yeah.
Now for some examples here. So Steph, are you in the mood for some examples, or do you want to lurk? Okay. So let's see here.
Oh, okay. Okay, sounds good.
Then that means
Yeah.
I'll give it a try.
Yeah. Yeah, I guess I can read this one. So like relation as a subset. Let A equal the set of 1 and 2. Oh yeah. And B equal the set of 1, 2, and 3. And define a relation R from A to B as follows. Given any ordered pair XY and A cross B, XY is in R means that X minus Y over 2 is an integer. Yeah, so just to quickly review, so the idea is that like a relation, so for example, the less than relation, it's intuitively just some way in which two things can be related. So like one number can be less than another. And then the formal mathematical definition is that a relation is a set of ordered pairs. So the less than relation is the set of ordered pairs where the first item is less than the second. And then so relation R is a set of ordered pairs. So something R something means that the corresponding ordered pair is in the relation. Yeah, so this relation we have defined there. So the first part is state explicitly which ordered pairs are in A cross B and which are in R.
Okay. So let's see. By the way, if anyone's lurking, if you say hello, I'll give you EXP in the gradebook.
Yeah.
But let's see here. So explicitly Witcher and A cross B. Okay, let's see.
Yeah, and so A cross B, so it's going to be the set of ordered pairs, set of all ordered pairs where the first item is from A and the second item is from B.
Okay, I just don't think that I copy and pasted it right. Oh, I see.
Oh yeah, I guess I didn't copy and paste the fraction bar there. But you could put a slash for that. X minus y. Yeah, so you have like parentheses x minus y and then that over 2.
Okay. So A cross B is gonna be one, one, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. I believe that's it.
Yeah. Yeah, that's all the possible ordered pairs where the first item is from A and the second item is from B. And then the book mentioned that like a relation like from a set A to a set B is going to be a subset of the cross product of A and B, because you're going to have some of those ordered pairs in the relation, but maybe not all of them.
Right? So is 1 R3? For it to be R, it means that x minus y divided by 2 is an integer. Well, 1 minus 3 is negative 2, divided by 2 is negative 1, so that is an integer.
Yep.
Negative 1 divided by 2 is negative 0.5, which is not an integer.
Yeah.
2 minus 2 is 0, divided by 2 is 0. I think 0 is an integer, right?
Yeah.
And now it says, what are the codomain? Okay. So the domain and codomain of R. I believe the domain is always whatever the first set is, and the codomain is always whatever the next set is.
Yeah. Yeah, exactly. Yeah, that's the case just by the definition of a relation.
Okay.
Yeah. And then there's one other part in part A, like that part can use part B. Like what are all the ordered pairs in the relation? And then 2 of them we know already are 1, 3, and 2, 2.
All right. What are all the ordered pairs in relation? So we know 1, 3 is in there, and 2, 2. So to be in the relation, x minus y divided by 2 has to be an integer. 1 minus 1 is 0. Divided by 2 is 0, so that's an integer.
Yep. So that'll be in there too.
Welcome to the stream, Gummy. Gummy ghosting. You just earned yourself some attendance points.
Yeah. Yeah, welcome. Yeah, exactly right. Yeah, 1, 1, that is going to be in the relation there.
So, I know Gummy from a server, so I guess I could explain this great book to Gummy offline. but it is pretty interesting. Um, well, I'm tempted to explain it again. So let's see. Gummy, what do you think about this? Um, we're looking for ways to improve the stream, make it a little bit more fun. It's a math stream, right? Not a gaming stream. So I want to like make it a little bit more fun. Um, so create this grade book, and basically you get EXP instead of a grade. Long story short, I'll give people rewards if they get a lot of EXP. Discord roles for the first few like important level ups, and then maybe some art pieces of their character persona for those like later level ups. For example, this masterpiece. Even if you want to lurk, you get, like passive EXP just from attendance. And the other stuff I'll go over later. But yeah.
Yeah.
Okay, where were we?
Oh yeah, the all the ordered pairs in the relation.
Looks fun, huh? Ordered pairs in relation. Right. So I was saying 1 minus 3, we got that one. 2 minus 1, that's not going to be 1 because 2 minus 1 is 1 and 1 divided by 2 is not an integer. 2, 2, we got that one. And then this is also going to be minus 1. This one would be 1, which would get us 0.5, that's not an integer. This would give us negative 1, which is negative 0.5, that's not an integer either. So I think this is it.
Yep. Yeah,
Okay.
that'll be all of them.
Okay. Maybe I should give myself points. I think I will.
yeah. The exercise.
True. So let's see here. I mean, normally I'll do this offline. Just so we see how it works. There we go. All right, perfect.
Yeah, and then we've got another one here, the circle relation. Yeah, and just to review for everyone. So a relation, it's intuitively like a way in which two things can be related. Like one number can be less than another. And the formal mathematical definition says that a relation is a set of ordered pairs. Like the less than relation would be the set of ordered pairs where the first item is less than the second. Yeah. So yeah, and then a relation from R, like here we have a relation from R to R. That means it's a set of ordered pairs where the first item in the ordered pair is in R, and the second item is also in R. And if you have a relation from one set to another, the first set is called the domain and the second one is called the codomain.
Okay.
Yeah, so let's see this when we got the circle relation.
Okay.
Yeah.
So, relation C from R to R as follows. For any xy in R cross R, x, y is in C means that x squared plus y squared equals 1.
Yeah. Yeah, it's called the circle relation because the graph of that equation would be a circle.
Okay. This is going to be really hard to copy and paste.
Yeah. Yeah, we could also kind of look at them here and then write the answers there.
Okay. So it's 1, 0 in C. B and C means that x squared plus y squared equals 1. Well, 1 squared is 1 plus 0 squared, which is 0, that does equal 1.
Yeah.
A.
Yeah, so that one is in C.
All right, now for the next one.
Yeah. And I guess those ones we could answer just like kind of yeah.
Okay. 0, 0 in C. Well, no, because 0 plus 0 does not equal 1.
Yeah.
Negative 1/2 and the square root of 3 over 2 in C. Well, negative 1/2 squared, I think, would be positive 1/4.
Yeah.
And the square root of 3 over 2 squared, I guess that would be 3/4.
Yeah.
Well, 1/4 plus 3/4 does equal 1, so this would be in C. Also, I don't want to show the solution.
Yeah.
So
Yeah.
let's see
Yeah,
here.
exactly. I see. It is.
Okay, now we have negative 2 squared, which is 4, plus 0 squared, which is 0. 4 does not equal 1, so that one's not in C.
Yeah.
And then 0 and negative 1. Well, 0 squared is 0, plus negative 1 squared, which is 1, equals 1. So that is in C. And then finally is 1C1. Well, 1 squared equals 1, and 1 squared equals 1, which equals 2 if you add them. And that does not equal 1. So it is not in C.
Yeah.
The domain and codomain, since it's a relation from R to R, then R is a domain and R is the codomain.
Yeah.
It says draw a graph for C by plotting the points of C in the Cartesian plane.
Yeah.
So,
So that one's harder to do. And
I mean, we do have this thing. Let's see here. So the Cartesian plane, what is the Cartesian plane? Is that?
that's like where you got the the x-axis and the y-axis. And you can plot points. So you have yeah, this one's kind of yeah, so you got the horizontal x-axis and the vertical y-axis. Yeah, these are kind of wavy lines though, but yeah, but yeah, it looks like that. And yeah, this one's kind of tricky, but what the graph is going to be, it's going to be like a representation of every point in the relation. So every point x, y, where x squared plus y squared equals 1. And it just happens that like x squared plus y squared equals 1, that's the graph is the unit circle, meaning it's the circle centered at the origin, the point 0 is 0 where the two axes meet, that has a radius of 1. So every point on it is a distance of 1 away from the origin. So like roughly it would look like that. Yeah, not that sort of circular, but yeah, it's supposed to be a perfect circle.
Okay.
Yeah. So it would it would be a circle of radius 1 centered at the origin, and that's that's kind of something hard to like kind of just figure out on one's own. It's kind of just like a thing to know that like x squared plus y squared equals 1. That's what its graph looks like.
Yeah.
In general, like if you have an equation like x minus h squared plus there's like this pattern. If you have x minus h squared plus y minus k squared equals r squared, then that's the graph of that is going to be a circle whose center is the point hk and whose radius is r, where the radius is the distance from the center to any point on the circle. And in this case, like x squared plus y squared equals r squared, that's like the same as x minus 0 squared plus y minus 0 squared equals 1 squared.
Right.
So it fits that pattern. But yeah, it kind of is like a good general math knowledge thing to know. X squared plus y squared equals 1 is the unit circle with radius 1 centered at the origin.
Okay. So what do they want us to do here? Draw a graph for C by plotting the points of C in the Cartesian plane.
Oh yeah, I guess by plotting points, well, I guess we can plot some easy points. Like we know that the point 0, 1 has got to be on the graph because 0 squared plus 1 squared equals 1.
Okay.
So we could like plot that point, and the point 1, 0 is going to be on there. Similarly, so we got 1, 0, because 1 squared plus 0 squared equals 1. And then similarly, 0, negative 1 is going to be on there. Yeah, exactly. A negative 1, 0 is going to be on there.
Okay.
Yeah, and then I guess, so those are some like easy ones to find, and then you can get the circle by drawing it through those points.
Okay. Well, let's call that one solved.
Yeah. Yeah. So that's the circle relation.
Okay. Now let's see.
Yeah, I can read this next part.
Go ahead.
So arrow diagram of a relation. Suppose R is a relation from a set A to a set B. The arrow diagram for R is obtained as follows. 1. Represent the elements of A as points in one region, and the elements of B as points in another region. 2. For each x in A and y in B, draw an arrow from x to y if and only if x is related to y by R. Symbolically, draw an arrow from x to y if and only if x r y, if and only if xy is in R. So the idea is that like the formal representation of a relation is going to be as a set of ordered pairs, but like a kind of more informal way of representing a relation is to have like you can draw two circles or two regions, one of them that includes all the elements in A, all the things in the set A, and one of them including all the things in the set B. And then you can draw arrows from for everything in A that's related to something in B, you can draw an arrow between them, going from the thing in A to the thing in B. So, for example, if you had like the less than relation, you could have like two circles with numbers in them, and then you could draw an arrow from 1 to 2, for example, because 1 is less than 2, so it's related to 2 by the relation. Yeah,
Okay.
so that's how an arrow diagram would work.
All right. Let's see here. So like if A is this, and this is like this, what do we do? Something like this? And then
Yep.
if R is the less than symbol, then 0 should point to all of them, right?
Yeah. Yeah, because 0 is less than 1, and 0 is less than 2, and 0 is less than 3.
1 just points to these two,
Mm-hmm.
and 2 just points to this. What about arrows going in the opposite direction? I guess that doesn't matter, right? Because we're only concerned with
Yeah.
okay, Doug.
Yeah, exactly. Yeah, they just go in that direction because that already tells you all the information you need to know what the relation is. It tells you what's related to what.
Okay. So
Yeah.
making a arrow diagram like this would be the equivalent of doing it in set roster notation. Is this set roster notation?
Uh, yeah, yeah, set roster, like where you list everything in the set. Yeah.
Okay.
Yeah, exactly. Oh yeah, it's good to see what it would look like as a set.
Nice. Okay, okay. So example. Let A equal 1, 2, 3 and B equal 1, 3, 5, and define relations S and T from A to B as follows. For all ordered pairs XY and A cross B, XY is in S means that X is less than Y. T equals 2, 1 and 2, 5. Okay, okay. So T is also a relation, but it doesn't have a formula, right? It's just
Yeah.
hard coded to ordered pairs.
Yeah.
Draw arrow diagrams for S and for T. Okay, let's see here. In that case, erase these, erase these, erase these, erase these.
Yeah, and this will be fun. Kind of like mathematical archery with the arrow diagrams.
Right. R is still less than, right?
Yeah. Yeah, or I guess it's called S instead of R this time.
Is it?
Uh,
S and T? Yeah, you're right.
yeah.
Oh. Let's see. Also, T. But how much time does this stream have left?
Uh,
It's like
yeah, I
what?
guess we could.
Like an hour and a few minutes?
Yeah,
Okay, okay.
yeah, that sounds good.
T equals 2, 1, and 2, 5.
Yeah. Yes, this is interesting. Like a relation doesn't need to have any defining pattern. Yeah, like Grayson mentioned, it could just be represented just as a plain set of ordered pairs.
Okay. And then A and B. 1, 2, 3, 1, 3, 5. I'll do S in light blue. And then I'll do T in green. So for T, the ones that are related, I mean, should be like this. For S, the ones that are related, would be like this. Oh wait, this one's also, and this one's also less than 5. So in this case, S ends up being looks about right.
Yeah,
Okay,
yeah,
let's
exactly.
see. Let's see.
Yep, so it's arrow diagrams.
Okay.
Yeah. Yeah, I guess I
And
could read this one too because that one was really short.
sure.
Yeah, so functions. In section 1.2, we showed that ordered pairs can be defined in terms of sets, and we defined Cartesian products in terms of ordered pairs. In this section, we introduced relations as subsets of Cartesian products. And thus, we can now define functions in a way that depends only on the concept of set. Although this definition is not obviously related to the way we usually work with functions in mathematics, it is satisfying from a theoretical point of view, and computer scientists like it because it is particularly well suited for operating with functions on a computer. Definition: a function f from a set A to a set B is a relation with domain A and codomain B that satisfies the following two properties. 1. For every element x in A, there is an element y in B such that xy is in F. So the ordered pair xy is in F. 2. For all elements x in A and y and z in B, if the ordered pair xy is in F and the ordered pair xz is in F, then y equals z. So it's worth discussing like kind of what that means. So firstly, a function is a special type of relation. where a relation from a set A to a set B is a set of ordered pairs where the first item in the pair is in A and the second item in the pair is in B. And what's special about this kind of relation is that everything in A is related to something in B. It's not the case that we have like some things in A that aren't related to anything.
Mm-hmm.
Yeah, so like intuitively, the idea is that like A is the input set and B is the output set. So every input you can plug into the function to get some output is intuitively the idea. But more formally, every element in A is related to something in B. So that for every x in A, there is some y in B such that xy is in the relation F. And
Mm-hmm.
then the second point says that this is a cool way of putting it. So if xy is in F and xc is in F, then y equals z. And that's just a fancy way of saying that every element of A is related to exactly one element of B and no more. So, like, if X is related to two different things, or sorry, if X is related to two things, Y and Z, then Y and Z have got to be the same because X can't be related to two different things.
Okay.
Yeah,
So in this case, since A is related to, or since A has 1 in it and 1's related to 3 and 5, then this S relation would not be a function, right?
yeah, exactly.
Also,
Yeah,
um, right, because it's related to two different things. And then for the T, we have elements in it that aren't related to anything.
yeah, yeah,
So
exactly. So there are two problems with T.
it's also not a function.
Yeah, yeah, one and three aren't related to anything, and then two is related to two separate things.
Hmm. Okay, okay.
Yeah, yeah. So not every relation is a function, but every function is a relation. A function is a special kind of relation.
I guess I could make an easy function, which was just, I mean, I guess it would be a function in this context, right? If I said, whoa, it's
Yeah, you
bad.
could say like, um,
I could just pair everything with one other thing,
yeah,
and then that would be a function, right?
yeah, exactly. Yeah, because everything in the first set is related to something. Intuitively, every input can be plugged in to get some output, and everything is related to just one thing and nothing more. So one is only related to one, two is only related to three is only related to five. Each of them is related to one thing and nothing else. And in fact, if you instead have like f equals the set of 1, 1, 2, 1, 3, 1, like if everything in A was related to 1, then it would still be a function. Because it's okay to, at least in terms of the definition of a function, it's fine to have the same output correspond to multiple inputs. You just can't have the same input correspond to multiple outputs. Yeah, so that would also be a function because going through the criteria for the function definition, everything in A is related to something because 1 is related to something, 2 is related to something, and 3 is related to something. And additionally, everything in A is related to just one other thing, to just one thing, not multiple things. Yeah,
Okie doke. Hmm.
yeah, and then it restates those criteria. So
Okay,
yeah,
let's see. That is a
Yeah,
very
proper.
fancy way of saying it.
Yeah, yeah, exactly. Like, yeah, this is a way of this is actually like a way in which mathematicians will say that there's exactly one thing. Like, if there are two, then they're equal. That's another
Right.
way of saying that there's only one. Um, yeah, so properties one and two can be stated less formally as follows, where properties one and two are the criteria for the definition of a function. A relation f from a to b is a function if and only if, number one, every element of a is the first element of an ordered pair of f, so everything in a is related to something. Two, no two distinct ordered pairs in f have the same first element. And that's another way of saying that you don't have like two ordered pairs where the same item in A is related to two different things in B.
Right.
Yeah, and in most mathematical situations, we think of a function as sending. Oh yeah, let's look at that.
Hmm.
Yeah, so if the one were related to multiple things, then you
Right.
no longer have a function.
Okay.
Yeah, yeah, and in most mathematical situations, we think of a function as sending elements from one set, the domain, to elements of another set, the codomain. Because of the definition of function, each element in the domain corresponds to one and only one element of the codomain. More precisely, if f is a function from a set A to a set B, then given any element x in A, property 1 from the function definition guarantees that there is at least one element of B that is related to x by f. Everything in the domain is related to something. And property 2 guarantees that there is at most at most one such element. So nothing from the domain is related to two separate things in the
Right.
codomain. And this makes it possible to give the element that corresponds to x a special name, um, because meaning that we can unambiguously refer to the thing that is related to x. Um, Notation: if a and b are sets and f is a function from a to b, then given an element x in a, the unique element in b, unique meaning there's only one, that is related to x by f, is denoted f of x. So f parentheses x, which is read f of x.
Okay.
Yeah, so that's cool. And here we got another example: functions and relations on finite sets.
Okay, let's see. Easier to copy and paste.
Yeah,
So let A equal 2, 4, and 6, B equal 1, 3, and 5. Which of the relations R, S, and T defined below are functions from A to B? Well, it's a function if everything in A is mapped to something in B. So we need 2, 4, and 6 to be mapped to something, and only one thing. So for R, 2 is mapped to something in B, good. 4 is mapped to something in B, great. 4 is mapped to something else in B, so this is not a function.
yeah,
This
yeah,
one
exactly.
says, for all x, y, in A cross B, x, y is in S means that y equals x plus 1. Okie doke. So S here looks like all the ordered pairs which make it true for y to equal x plus 1. So y is from B and x is from A. So 2 and 3 works because 2 plus 1 equals 3.
Yep.
4 and 5. But there's no 6 and 7. So that means that not everything from A is mapped to something in B. So this is not a function either.
Yeah.
At least it's not a function from A to B.
Yeah, exactly. Oh yeah, that's an important point. Yeah, because like if A had just been the set of 2 and 4, then we
Then
would
this
have a
would have been
function.
correct.
Yeah.
T is
Yeah,
defined by...
so whether
Oh, go ahead.
oh yeah, so whether something is a function depends on like what the A and B are.
Mm-hmm. Whether or not something is a function from, yeah, a set to another set depends on those two attributes.
Yeah.
Depends on those two
Yeah.
conditions being met. But let's see. So T is defined by the arrow diagram. Okay. Well, everything in A is mapped to one thing in B. One and only one thing. So T would be a function.
Yeah. Yeah, would.
Alright, T is a function. S is not a function. R is not a function. Okay. More examples here. Looks like 2 examples. So in example 1.3.2, the circle relation C was defined as follows. For all x, y, and r cross r, x, y is in C means that x squared plus y squared equals 1. Is C a function? If it is, find C0 and find C1. So is C a function? So is everything in R mapped to something else?
Yeah, so is it the case that like any x you can plug into that equation corresponds to exactly one y?
Equaling 1, 2, right?
Yeah, yeah, where the equation ends up being true, so the sum of the squares equals 1.
I mean, I guess that's clearly false because, like, if you put 100 in here and 100 in here. Oh, wait, no. If you put 100 in here, actually. Or if, let's
Yeah,
say
like if you
if you put 10 in here, you would get 100. In order to get
yeah,
1, we would need 99. Negative 99.
yeah,
But
yeah,
you can't square anything to get a negative number.
yeah. Yeah, exactly. Because we're just working with x, y is in r cross r, so we're just working with real numbers. And I guess there are imaginary numbers where if you square them, you can get a negative number, but you can't do that for real numbers. So
Are
yeah,
there
because like
are there imaginary numbers that you can square to get negative 99?
uh, yeah, I guess there would be, but not in R, because like R is just the real numbers. But yeah, I guess there would like the uh like in the imaginary numbers, I is the square root of -1, and so like uh the square root of 99 times I, if you square that, you would get -99. um but uh but yeah, we can't do that here because we're just working with real numbers. Yeah, so if you plugged in 10 for x, there wouldn't be any y that you could get corresponding to that, to make x squared plus y squared equals 1. So like 10 is not related to anything, so this isn't a function, because not everything in the domain is related to something.
Is the square root of 99 times I in the imaginary numbers? Or
Yeah.
the imaginary numbers isn't just a set of like one number, which is I.
Oh yeah, yeah. It also has like different multiples of I, and I guess more generally, the complex numbers are defined to be the set of every number that is of the form real number plus real number times I.
The complex numbers. So is the complex numbers a subset of the imaginary numbers?
I guess I guess
No.
there's like yeah, the
Or
imaginary or what's often called the purely imaginary numbers. The purely imaginary numbers are like the numbers that are like a real number times I, and then that would be a subset of the complex numbers because the complex numbers are numbers of the form real number times I plus real number. And the real numbers will be a subset of the complex numbers because every real number is equal to a real number plus 0 times I.
times I? Oh, 0 times I. Gotcha.
Yeah, because that would just be 0.
Interesting.
Yeah. But yeah, imaginary numbers and complex numbers are cool, but
They're
because we
not.
just got real numbers here, we can't square anything to get a negative.
My last like unimportant question is why is it not the case that the imaginary numbers and the complex numbers are equal?
Oh yeah, I guess it's kind of just like a matter of definition. Like the set of uh, or I mean, sometimes I think I might have occasionally heard like imaginary numbers kind of used interchangeably with complex ones, but like the usual definition is like the purely imaginary numbers. Those are the set of numbers such that they're equal to a real number times I. The
Real
complex
number
numbers are
times.
equal to a real number times I plus a real number. So for example, 2I plus 4 would be a complex number, but not a purely imaginary number
You said
because
two
it
I.
doesn't,
Okay, plus 4.
yeah. So that would be a real number times I plus a real number. So that's a complex number, but it's not a purely imaginary number because a purely imaginary number would have to just be a real number times I.
Um, wouldn't a real number times I plus a real number equal some real number times I?
Uh,
Or
uh,
maybe not, right? Because
yeah,
if
not
you.
necessarily.
Okay. Because if you multiply
Yeah,
a real number by I, it's always imaginary.
yeah, unless you're multiplying 0 by I, that'll be the only exception.
But
Or I guess it would also be imaginary. I guess it would be imaginary and real actually. 0 I.
but if you multiply R a real number by I and add a real number, it's not always imaginary.
Not always, because yeah, like 4I plus 2 that isn't equal to just a real number times I. It's a real number times I plus 4 and that can't be expressed as just a real number times I.
A real number times I. So it would it be an imaginary number?
It would be a complex number because like the complex numbers are real numbers times I plus real numbers. So
Oh,
2I plus 4 would be a complex number, but it wouldn't be a purely imaginary number because it doesn't just equal a real number times I.
interesting. So an imaginary number plus a real number is neither imaginary nor real, right?
Yeah, yeah, or yeah, unless you're doing a real number times I plus 0.
Right,
Um,
right, right.
yeah. Oh, and hey, Sushi. Thanks for joining.
Up sushi. So let's see here. It's a
You know,
point
we're
for
looking at
sushi.
relations and functions.
Let's see. Yeah. From the looks of it, looks like sushi might be in first place. All this extra credit helped me with the stream, but I gotta go back and look at all the exercises. I know Steph did a lot, but yes.
Yeah.
So, did we do these? I don't think we did.
Oh yeah, we did part A, and then now we're on part B.
So, let's see. Define a relation R to R as follows. For all x, y, and R cross R, x, y is in L means that y equals x minus 1. Is L a function? If it is, find L0 and L1. Well, I think it is a function because for every x in R, there is a y that is one less because they both go on for infinity.
Yeah.
So for
Yeah, exactly.
L0, we would get -1, and for L1, we would get 0.
Yeah. Yeah, exactly. And then also, by the way, the other criterion for the definition of a function is that like every in this case, every x has to be related to exactly one y and no more than that. And that is
Oh,
also true because like for every real number x, there's only one real number that's one less than it. So that criterion is also met.
yep.
Yeah.
Okay, C is not a function. Um, Observe that there are many real numbers x such that x, y is not in C for any y. Right. But then they give us
Yeah.
this image. So let's see, what does this image mean here? The graph of C, it's a circle. Okay. And then there's points here that are on the circle. Okay, but there's a X out here.
Yeah. So this
Um,
is like something called the vertical line test. Like if you have a graph of a relation, where the graph of the relation would be a representation of all the points that are in the relation. So if you have a graph of a relation and you can draw a vertical line that intersects it at two different points, then the relation isn't a function because what that means is that you have an x value
right.
corresponding to two different y values.
1/2 is corresponding to both √3/2 and -√3/2.
Yeah.
It fails the vertical line test. Okay, Sushi knows this. Let's
Yeah.
see. It's gonna be interesting when this gets hard enough that like people don't know what's going on. I can't wait for that.
Yeah.
Well, let's see here. Okay, and when x is 2, there's no real number y such that it's on the circle, right?
Yeah. Yeah, so some x values don't correspond to any y values. They aren't related to any y values by that relation.
There's
Yeah, so
not.
it fails both of the criteria for a function.
Okay.
Yeah, and then this other one, we have the relation consisting of the ordered pairs where y, the second component, equals the first component x minus 1.
Right.
Y equals x minus 1, and then the graph is a line. And well, that passes the vertical line test because so it meets the first criterion for the definition of a function. There's no, you don't have any x value that's mapped to two different y values. Um, and it also satisfies the other criterion, which is that um, every every item in the first set, in this case, every x value, has to be related to something. And in fact, yeah, in this graph, the line is going to extend forever in either direction. So, um, you do have every x value corresponding to some y value.
Nice, nice. So when x is 0, y is -1, which I guess is this point. When x is 1, y is 0, which is supposed to be this point. And when x is 2, y would be 1, which is somewhere in here. Okay, cool, cool. It passes the vertical line test. Function machines. Another useful way to think of a function is as a machine. Suppose f is a function from x to y, and an input x of x is given. Imagine f to be a machine that processes x in a certain way to produce the output f of x. This is an illustration in figure 1.3.1 on the next page. Okay, so you put the input x into the function machine and you get f of x. That's how a function works. Example. Functions defined by formulas. So the scoring function f from r to r is defined by the formula f of x is equal to x squared for all real numbers x. This means that no matter what real number input is substituted for x, the output of f will be the square of that number. This idea can be represented by writing f of blank equals blank squared. In other words, f sends each real number x to x squared, or symbolically, f sends x to x squared. Note the variable x is a dummy variable. Any other symbol could replace it as long as the replacement is made everywhere the x appears. Okay. The successor function g from z to z is defined by the formula g of n, take your time sushi, equals n plus 1. Thus, no matter what integer is substituted for n, the output of g will be that number plus 1. Okay. G of blank equals blank plus 1. In other words, g sends each integer n to n plus 1, or symbolically, g sends n to n plus 1. An example of a constant function is the function h from q to z, defined by the formula hr equals 2 for all rational numbers r. This function sends each rational number r to 2. In other words, no matter what the input, the output is always 2. So h of blank equals 2, or h sends r to 2. The functions f, g, and h are represented by the function machines in figure 1.3.2. I guess they just arbitrarily picked the sets for these functions, since I could see the functions working for other sets besides these.
Yeah.
Okay.
Yeah, definitely. Yeah, I could have like a constant function that sends every real number to 2 rather than just every rational number.
Yeah, or every imaginary number to 2.
Yeah. Yeah, exactly.
A function is an entity in its own right. It can be thought of as a certain relationship between sets or as an input-output machine that operates according to a certain rule. This is the reason why a function is generally denoted by a single symbol or string of symbols, such as f, g, or log, of log, or sin. This is or log. A relation is a subset of a Cartesian product, and a function is a special kind of relation. Specifically, if f and g are functions from a set A to a set B, then f equals the set of all ordered pairs in A cross B such that y is equal to f of x. Okay. Oh. And g equals the set of all ordered pairs x, y in A cross B such that y is equal to g of x. Okay. It follows that f equals g written f equals g if and only if f of x equals g of x for all x in A. Okay.
Yeah. Yeah, so two functions, like if they to be equal, they've got to have the same domain and codomain, and then for any input, you got to get the same output for each of them.
But what if the domain of G was bigger than the domain of F, but F's domain was a subset of the domain of G?
Yeah, and I guess technically they wouldn't be equal because um, they have to have the same, like everything about them has to be the same for them to be equal. So that's why they specify that, like, specifically if f and g are functions from a set A to a set B, then they're equal in this case if f of x equals g of x for all x in A. So they, in addition to having every output map to the same, or sorry, every input map to the same output, they've got to have the same domain and codomain.
Okay.
Yeah. Yeah, then we got an example here. Um,
So let's see. Define F as, well, F sends R to R and G sends R to R by the following formulas. F of x equals the absolute value of x for all x in R. G of x equals the square root of the square of x for all x in R. Does F equal G? Well, they both have the same domain and codomain.
yeah,
Let's see.
yeah. So we got that, and then we got to check whether for every x in R, f of x equals g of x. So in other
Well,
words, we got to figure out whether it's always the case that for any real number x, the absolute value of x equals the square root of x squared.
Okay, well, the real numbers stretch out from negative infinity to positive infinity. So for every x in the real numbers, you would get, the positive square. Oh, wait, no. Oh, you would get the positive version of it because we're dealing with absolute value here.
Yeah, yeah, or the
So,
non-negative version, because I guess technically zero. The absolute
right,
value of zero is zero,
which
which is
isn't.
not technically, yeah, not quite positive, but non-negative.
So let's see. In this case, for every negative number, if you square it, you will get the positive square. And then if you get the root of that square, you would get the original number, but in its non-negative form.
Yeah, yeah, and that would be the absolute value.
Including for zero, right? Because the square root of zero is zero.
Yeah. Yeah,
Okay.
and then for positive numbers, you square them and take the square root. You're also going to get, in that case, you'll just get the number back, x, and the x would be equal to its absolute value for a positive number. Um, yeah,
Okay. Does f equal g? It does.
yeah,
Because the absolute value of any real number equals the square root of its square. Now
yeah,
test yourself. Okay, I think that we might almost be done with this. Let's see here.
yeah. That's all of chapter one. Yeah, congratulations everyone for finishing the first chapter.
Oh, really? Now, hmm. So, what should we do with the little bit of extra time we have here? Like, ordinarily, I guess I would ask the audience if anyone wants to farm any of these for some quick EXP. Before ending the stream, because I don't want to go into chapter 2 this stream. I mean, while we think about that, I guess I can go ahead and knock these out. Let's see. Given sets A and B, relation from A to B is... It is... a subset of ordered pairs from the set of ordered pairs A cross B. Such that, you know... I think that should be it for the definition, right? Because...
Yeah. Yeah,
Okay.
exactly. It could be any subset of A cross B. So yeah, it would be a subset of A cross B.
Okay.
And then a function will have further restrictions.
So a function f from A to B is a relation from A to B that satisfies the following two properties. For every element x of A, there is a corresponding element y from B
Yeah, and it's corresponding in the sense that x is related to it.
Right, such that x
by
is
f.
related to it by f.
Yeah. So you can say like there is an element y of B such that one way of putting it would be fxy, or sorry, xfy.
Or like...
Yeah, there's another way to put it too.
Is that?
Yeah, you could say xfy, or yeah, you could say f of x equals y. You could also say like xy is in f. Yeah, although I guess f of x equals y might kind of assume that we already have a function.
True.
Yeah, so xfy or equivalently xy is in f.
Let's see. For all elements x and A and y and z and b. Oh, this is the fancy one.
Yeah.
So we're trying to say there's just one. So if there's two, then they're equal. So like if...
Yeah, so it's like if x is mapped to both y and z, and that can be expressed by saying like if xy is in f and xz is in f.
Right. No.
Yeah. And then...
Right. And then y and z are equal.
Yeah, so y equals z.
If f is a function from A to B and x is an element of A, then f of x is function from A to B and x is an element of A, then f of x is... Oh, an element of y. Alright, an element of B.
Yeah, it's an element of B, and I guess it's like an element of B such that I guess f of x is in f.
Right.
Yeah, it's like that. It's the element that's related to x by the function.
So isn't the term f of x, doesn't that imply that f of x is an f?
Yeah, I guess it kind of does. Yeah. Um,
You could say it such that f of x is in.
oh yeah, I guess, and it's like not quite f of x is an f, but the ordered pair x comma f of x is an f.
Wouldn't that also imply like the ordered pair x comma f of x would imply like this seems like the use of f of x implies that x comma f of x is in f.
Yeah, yeah, it kind of does. I guess because let me see. I wonder what did the book say when they introduced f of x? So I
Right.
guess they say the unique element in V that is related to x by f. That's how they put it. Um,
Hmm.
so I guess that's another way of saying it. Like, yeah, the unique element of B um, that's related to x by f.
Okay. So that f of x is a unique element of b such that what?
Um, uh, the unique element of B that is related to x by f.
Okay, okay. Okay.
Yeah, but I guess another way of putting that would just be to say like x comma f of x is in f.
X comma f of x is an f. Yeah, there should be answers right somewhere.
Yeah, I
Yeah.
think they're at the bottom, right below exercise set 1.3.
The unique element of b that is related to x by f. Oh yeah, that's what you said.
Yeah.
Subset of the Cartesian product AB. Okay. An element y of b such that the ordered pair
Okay, that's what
x,
we
y,
have.
and f. Okay. Now, I think that we are done with the math for today. And we can just sit and think for a minute before ending stream. Hmm. Specifically, I'm thinking of ways to improve the stream, to improve the experience for people watching, and for ourselves as we get through the book.
Yeah. Yeah, so definitely let us know if there's any way we can improve. You can let us know in the chat or you can let us know later if you think of anything.
Yep, the question goes out to you lurkers as well. But it's for us too. I want us to think about it as well, Whitaker.
Yeah. Yeah, well, I do like the idea that you mentioned earlier of kind of looking at the section beforehand and kind of teaching it without reading it. Um, I guess to do that we could use like I guess use the whiteboard and kind of explain the concepts there. Um,
Hmm.
yeah, we could still do some exercises from the book if we do that.
Right?
kind of have the explanation in our own words.
Hmm. Yeah, it could work. I don't know. We'll see. It'll take significantly more effort, but maybe that'd be entertaining. But I don't
Yeah,
know. Maybe not.
yeah,
We might just read through the whole book. I'm definitely absorbing it. Oh, it's
yeah.
fair. Our complex number is going to be relevant next time. You were discussing it earlier. Well,
Oh,
first, yeah.
yeah,
Welcome to the stream, Fair. You want to answer that? I'll give Fair an
yeah,
attendance point.
yeah, yeah. Welcome, Farah. Oh, yeah. I guess they're not actually going to be involved next time. We kind of just we're discussing them for fun a bit because the concept came up that you can't square a real number to get a negative number, but you could square a complex number to get a negative real number. Yeah, so it just kind of came up in relation to one of the examples, um, but yeah, next time chapter 2 starts covering propositional logic, which is looking at kind of how the truth value of complex statements is related to the truth value of its parts. So like if P and Q then not R, how is the truth or falsity of that related to the truth or falsity of its component parts? So we'll be starting to look at logic next time.
You have an exceptional memory, Whitaker.
Oh, thanks.
Also,
Yeah.
that was an interesting question. Are you interested in complex numbers, Fair? They're definitely fun to talk about. See?
Yeah. Yeah, they are cool. I think they have some applications like in electrical engineering or some
Really?
areas like that. I don't really know how the applications work, but I've heard that. Um, yeah, but yeah, logic is gonna be fun too because it kind of like logic. It's useful for math, but it also has applications in all sorts of areas of everyday life because like we use reasoning all the time, and logic kind of helps us uncover the structure of reasoning and um, under what conditions a statement with a certain form is true or false. And so it can be kind of cool in that way to really look at the structure of reasoning.
Hmm. It's been a minute since I saw them. I would have asked for a review. Oh. Let me throw a question out to you guys lurking in the chat then. Like, how comfortable are you with, I guess, math in general? On a scale 1 to 10? So 10 would be like you read 12 math books, you've taken all of these courses. This is like graduate level stuff at 10. 1 would be like if like a middle schooler asked you for help on their math homework, you wouldn't be able to help them. You know, you would get stuck by the fractions, like 12 divided by 5. It would just demoralize you. 5 would be like, I don't know, maybe you read a book like this one already. Or you're a pretty solid student, you know? You know, some students are pretty just like solid. So that would be like a 5. Personally, I'm pretty rusty. I think I could like reason my way through some middle school math, even if I forgot the concepts. So I think I'm like at a 3 right now. Hoping this book bumps me up to like a 6.
Yeah,
5, 6. Yeah. Okay.
yeah, yeah,
Hmm.
yeah, I don't know for myself. I guess um, maybe like 7 or 8 or something because I majored in math as in college.
Yeah.
So I took some more advanced courses. I guess they're like more advanced courses that I could have taken but didn't. But I took like abstract algebra and real analysis. So yeah, probably like 7 to 8 somewhere in that range. Like
S-
I haven't taken graduate level courses though, so
Right.
um, yeah, maybe like a 7 or something like that.
Oh. One thing I'm like constantly haunted by is how it teach someone who's at a one. Like there's something magical and noble about teaching someone who's at a one and helping them like follow along. There's a lot of basic stuff that they would need to kind of understand though. Like they might not know what x squared is or what a variable is or how to think about those things. Um, you
Yeah.
probably couldn't teach someone who's at a one during a stream. I mean, unless it was like a really long stream, like a 10-hour stream and it was really chill, like you weren't trying to get through something under a time limit.
Yeah.
But
Yeah, but that is kind of yeah, would be definitely a rewarding and good experience to kind of really kind of teach someone sort of from scratch, like mathematical reasoning.
mhm.
Yeah, yeah, definitely is a good thing to do.
Yeah, I don't know. We'll see. So far, it seems like the people who show up to these streams were like pretty good. But you don't
Yeah.
have to be, Feel free to be like, just like a five. I'm that deplorable Swiss cheese that only remembers what's relevant to me and forgets the basics. Aren't we all?
Yeah. Yeah, like that way of putting it.
Still pretty good. Interesting. Now, if you're
Huh.
just got here, just trying to get by, welcome to the stream. Let me give you your attendance point here.
Yeah, welcome. Thanks for joining.
So we finished the math portion of the stream. Now we're just kind of chilling. Trying to think of how to make it stream like this a little better. Let's see. Just trying to get by. How comfortable do you think you are at math? Going from like a 1 to a 10, like on a scale 1 to 10? 10 is like, your graduate level math. 1 is like you couldn't hang with the middle schoolers' homework. A 5 is like you're a pretty solid student. Like you've probably read a book like this. Hmm. And then anyone lurking in the chat, if you guys are complete trash at math, feel free to just lurk and enjoy the music.
Yeah.
7, probably. Haven't done math in a while, but concepts should come back easily. 7's pretty high.
Oh, great. Yeah,
Yeah.
that's impressive.
I wonder what it's like to lurk to a stream like this. If you're like doing something else, like writing a report, I guess it's just music and a constant stream of voices and
Yeah.
pretty math heavy majors. That helps.
Oh,
Oh,
cool.
what would you say your major was? I don't think these guys know. It's kind of cool having a geophysics thing.
Oh, wow. Wow, that's impressive.
It's kind of cool having a stream with so many math heads. Are any of you guys like not math related? You know, do I have any artists out there? Oh yeah, fair. What's your math backstory? What's the lore behind that? Uh, complex numbers. We also have a Discord. Feel free to pop in if you're above 18 years old.
Yeah, definitely. Stop by.
Let's see. So let's see, Whiticker. What do you think the ideal outcome would be for a grade book like this? What would be the most beautiful thing to see in a couple of months or a year?
Yeah. I guess, I mean, kind of just partly kind of enjoying kind of just um, sort of the beauty of the subject and like, and the logic of it. But I guess, yeah, through this book, one could develop, really the foundations of mathematical thinking, and kind of open up a new way of, a new way of reasoning would be opened up to you. So, so that would be a certainly a valuable outcome because this book is, really the foundations of advanced math. Like what you need in order to study subjects like abstract algebra or real analysis or mathematical logic, and things like that. So a lot of other more advanced math will be opened up to you, and it would also just be this new way of thinking, and it would also probably like make your reasoning more precise in other areas. Like if you're not accustomed to mathematical proofs, uh, getting practice with them could just lead you to really think about, in each case, like does this claim follow from this one? Like how can I precisely make my points? And yeah, kind of just can absorb into all sorts of other areas as well. This kind of um, way of thinking. Yeah, but I guess yeah, it just kind of is a good way of kind of seeing what advanced math is all about. And yeah, so that would definitely be valuable. Um, this is it's a lot different from like elementary school or high school math, where it's a lot of calculations and graphing and things like that. This is more abstract and foundational, so it's definitely a different kind of math. So it's definitely a valuable subject to learn.
Oh, that was a way
Yeah.
better. Go ahead.
Oh, I was gonna say, I think it's actually, at least for me, it's a lot more interesting than high school math.
True. Oh, that was a way better answer than I was um anticipating. I just meant like, oh, welcome back, Sushi. I
Yeah,
actually
welcome
meant
back.
like, what do you think the most ideal outcome would be for this little like grade book I have here?
Oh, the grade book. Oh yeah. Well, okay, so it would motivate people to come to the streams and get some practice. And it'll just make the experience more fun. So yeah, maybe people would be able to get into the higher ranks. And maybe even get some of the art pieces. So that'll be fun. Yeah, maybe we could also kind of help motivate the audience, help grow the audience. That's kind of a unique, fun kind of game like aspect to it.
Yeah. Wonder like after like 6 months or a year, what would the ideal grade book look like?
Yeah, well, maybe we'd have some people in the upper ranks, I guess, um, like the blacksmith or the ones that are that would get the art pieces even. Yeah, I guess we just have some people like ranked pretty high.
Okay, let's see. Well, you made it just in time, Sushi, for the absolute end of the stream because we are out of time. So, yeah, I think it's time to end it.
Yeah.
Does anyone have any last words? Mine are just, if you want, join the Discord. I love you guys.
Yeah. Yeah,
That's
thank you so much for coming, everyone.
yeah. That's totally fine, Sushi. Look at all that extra credit, like you've done so much.
Yeah.
Yeah.
Yeah. Yeah, that was fun. Yeah, thanks so much, everyone. Hope you have a wonderful night and great day tomorrow.
Yep. See you all later.